Hello everybody, today I will make a summary about oxidation reduction reaction. What do we mean by oxidation and reduction? Oxidation means the loss of electron. For example, if we have zinc metal can lose 2 electrons to become Zn2+, it becomes ion. This reaction is an oxidation half reaction. So since zinc undergoes oxidation, it is known as reducing agent or reductant. While reduction is a gaining of electrons. For example, if we have CO2 plus can gain 2 electrons to become a metal. So ion becomes a metal. CO2 plus gains 2 electrons, so it is called an oxidizing agent or oxidant. Let's consider a reaction between metal and metal ion. For example, if we have a beaker containing silver ions, solution containing silver ions, and we put in it a zinc strip, a reaction can take place between Zn with Ag+. So Zn will change into Zn2+, and Ag+ will become Ag. So we have many observations. The mass of zinc strip will decrease with time. The concentration of Ag plus ions will also decrease since it becomes Ag, and a silver deposit will appear on zinc strip. The reducing power of zinc will be greater than we compare metal with metal. So the reducing power of zinc will be greater than the reducing of Ag. While we compare ion with ions, and the oxidizing power of Ag plus is greater than Zn2 plus. So if we put an axis of electrochemical classification, this axis is written as this is the increasing order of reducing power, and this is the increasing order of oxidizing power. If we arrange the two metals, we know that the reducing power of zinc is greater than the reducing power of Ag, so Zn will be lower than Ag. Also, we know that the oxidizing power of Ag plus is greater than Zn2 plus, so Ag plus with Zn2 plus. This is the electrochemical classification of these of the two redox couples. The two redox couples involved in this reaction are Zn2 plus Zn, Ag plus Ag. Always the redox couple is written as ion metal. You should always write it as ion metal in this case. The oxidation half reaction, zinc will become Zn2 plus by losing 2 electrons, while Ag plus will become Ag plus by gaining 1 electron. So the overall equation is the addition of the two equations, but we should take care of the number of electrons. In the first equation, the number of electron is 2, while here we have 1 electron. So multiply all the equation by 2, and we add them to get Zn plus 2Ag plus, it gives Zn2 plus 2Ag. Here is the electrochemical classification axis of some redox couples. A spontaneous reaction can take place between strong oxidizing agent and strong reducing agent. Here this is the oxidizing power and this is the reducing power. So a spontaneous reaction between strong oxidizing agent and strong reducing agent according to gamma rule. For example, if we take, let's take some examples. If we take Au3 plus with Ag, Au3 plus with Ag, start by ion always. Au3 plus with Ag, gamma rule is satisfied in this case, so a reaction can take place. But if we take, for example, Al3 plus with an I, Al3 plus with an I, this is the ion, start by ion. Al3 plus with an I, the gamma rule is not satisfied, so no reaction can take place. A third example, if we take, for example, Cu2 plus with Pb, lead, Cu2 plus with lead, a gamma rule is satisfied, so a reaction can take place. Another type of reaction can take place between acid and metal. Let's know what's the meaning of an acid. Acid is a chemical compound that can dissociate in water to give H plus ions. For example, if we have hydrochloric acid, which is HCl, when it is put in water, it can dissociate to give H plus and Cl minus ions. But another example, H2SO4, which is sulfuric acid, when we put it in water, it is dissociated into 2 to give 2 H plus ions with SO4 2 minus. The redox couple of acid is written as H plus H2 since hydrogen gas is released. So when an acid is reacted with a metal, hydrogen gas is always released. An example is a reaction between aluminium and acid. Any acid of them, HCl or H2SO4, we take only H plus. Aluminium is a metal that can lose 3 electrons to become Al3 plus, which is the oxidation half reaction, while H plus ion can gain 2 electrons, 2H plus ion gains 2 electrons to become H2. Let's review this reaction. H plus becomes H2 during this reaction. H plus will gain an electron plus with electron, but since we have H2, so we should multiply H plus by 2. So here we have 2 plus the number of electron will be 2. This is the equation. By adding the two equations, we can notice that the number of electrons is 3 electrons and here it is 2, so they are not equal. To make them equal, we should multiply the first equation of aluminium by 2 and the second equation is multiplied by 3, so we get 6 electrons. Before adding them, we multiply aluminium equation with 2 by 2 and reduction half reaction by 3, so the overall equation will be as follows. I will start solving some examples or some parts of the bi-weekly worksheet, which is a revision for the exam. With respect to exercise 1. In exercise 1, we have 3 experiments. In the first experiment, experiment A, we have a solution containing Ag plus and we put in it nickel strip. In experiment B, we have a hydrochloric acid solution and we put in it silver strip. In solution C, we have Cr3 plus ions in a beaker and we put in this solution Zn strip. Do we have a reaction in experiment A? According to this electrochemical classification, Ag plus is the ion that can react with Ni according to gamma rule. So a reaction can take place in beaker A. In beaker B and C, the observation were given. In beaker B, we don't have any change, so no reaction can take place. But in beaker C, the green color of the solution fades with time. The green color of the solution is the color of Cr3 plus ions in it. So since this green color is fading with time, so Cr3 plus are becoming Cr, so a reaction can take place. To place the couples Zn2 plus Zn and H plus H2 on an axis of electrochemical classification, let's start by beaker C. In beaker C, a reaction is taking place between Cr3 plus and Zn. So the reducing power of zinc is greater than that of Cr. According to this electrochemical classification, this is the increasing order of reducing power, so zinc will be below Cr in this classification. For beaker B, we don't have any change, so we don't have a reaction between H plus and Ag. No reaction is taking place. So the reducing power of Ag is less than the reducing power of H2. To have the correct position of H plus H2, we have a note given in this exercise that indicates that we have a reaction between H plus and Ni. This note is given in this exercise. We have a reaction. Since we have a reaction, so the reducing power of Ni is greater than that of H2. As a summary, the reducing power of Ni is greater than H2, which is greater than Ag. So the redox couple H plus H2 will be between Ag plus Ag and Ni2 plus Ni. This is the solution of part which is about the position of the redox couples. With respect to part 23, we have to choose the correct answer and correct the false one. Ag plus is more oxidizing than Ni2 plus. By referring to the electrochemical classification, this is the increasing order of oxidizing power. So it is correct that the oxidizing power of Ag plus is greater than that of Ni2 plus. So this statement is true. For the second treatment, chromium ion Cr3 plus undergoes oxidation by gaining through electrons. Cr3 plus becomes Cr when it gains 3 electrons. This is correct, but this reaction is known as reduction. So we should change oxidation into reduction. For part 3, if hydrochloric acid is replaced by sulfuric acid, a reaction will take place. We should know that hydrochloric acid and sulfuric acid, these acids, the two acids contain H plus, and H plus is the ion that can make reaction with the metal. So if H plus, which is present in hydrochloric acid, does not make a reaction with Ag, then also H plus, which is present in H2SO4, will not make a reaction. So this statement is false. No reaction can take place. For this part, we have a beaker. Let's make a summary. We have a beaker containing 200 milliliter of a chromium nitrate solution of concentration. We should put a correct given. For this solution, which is Cr3 plus, we have volume equal 200 milliliter. Change it directly into liter by dividing by 1000. So it is 0.2 liter, and the concentration is equal to 1 mole per liter. We add a certain quantity of zinc. So the solution contains Cr3 plus, and we add a certain quantity of zinc. At the end of reaction, we noted that the number of mole of Cr3 plus is 0.0666 mole. So at time equal 0, the number of mole of Cr3 plus can be calculated according to this relation: N equal concentration times volume, where concentration is equal to 1 mole per liter and the volume is 0.2. So the number of moles of chromium ion Cr3 plus at time equals 0, يعني initially introduced, is 0.2 mole. At T final, it is given that the number of mole of Cr3 plus is 0.0666 mole. We have to write the two half reactions and deduce the overall one. The two half reactions, first we have a Cr3 plus can gain 3 electrons to become Cr. Since we have gaining of electron, it is reduction half reaction, while zinc will lose 2 electrons to become Zn2 plus, so it is oxidation half reaction. Before adding the two reactions, we should multiply the reduction half reaction by 2 and the oxidation half reaction by 3, so that the number of electrons are equal, and by adding them we get the overall equation. But the part 2.2 is an important part. How can we specify the limiting reactant? By comparing the number of chromium ions at time equals 0 and number of chromium ion at T final, we notice that a certain quantity of Cr3 plus remained unreacted. So Cr3 plus is not consumed totally. Since it is not consumed totally, this means that it is excess. Cr3 plus is the excess reactant, so zinc is the limiting one. So by this way we can determine the limiting reactant. How can we show that the concentration of zinc ions at the end of reaction is 1 mole per liter? Here we should take a stoichiometric ratio, but the only given we have is about Cr, and Cr is an excess reactant. How can we make a stoichiometric ratio between an excess reactant to get Zn2 plus? The stoichiometric ratio can be written as, since Cr is excess, so we should take the number of moles of Cr3 plus reacted over 2 is equal to the number of mole of zinc ions over 3. Number of mole of Cr3 plus reacted can be calculated, since we have at time equals 0 number of mole of Cr3 plus, and at T final. At T final, it means that the number of mole of Cr3 plus remained. This is the quantity remained. And as we know, number of mole reacted is number of mole initial minus number of mole remained. So it is 0.2 minus 0.0666. It will be 0.134 mole. This is the number of mole of Cr3 plus reacted. Substitute in this stoichiometric ratio 0.134 over 2 equal number of mole of Zn2 plus produced over 3. Thus, number of mole of Zn2 plus by calculation is 0.2 mole. This is the number of mole of zinc obtained. Concentration of Zn2 plus equal number of mole over volume 0.2, and the volume of the solution is the same, it is 0.2, so it is 1 mole per liter, so it is proof. How can we plot the curve that shows the variation of the number of moles of Cr3 plus with time? We have to draw the shape of the curve. We don't have accurate values for all times. The only two values we have is about time equals 0 and T final, but we don't know at which time this reaction is ended. Yani, is it we can't know the time, the accurate time. So to plot the curve, we time is always, we have the time and we have the number of mole of Cr3 plus. At time equals 0, we have the quantity of Cr3 plus ions 0.2. During reaction, it decreases till it becomes at T final 0.066. So it increases and it will remain constant at 0.06. So it is an excess. In some cases, with respect to this equation, the same equation, chromium with zinc, in some cases we are asked to draw the curve representing, for example, the number of mole of Zn with time. How can we draw this curve? For example, always write time with number of mole of zinc. Since Zn is limiting, we start by a certain quantity which will be given in the exercise, and it should reach zero at the end of reaction since it is limiting. But if we are asked to write or to draw the curve of representing, for example, zinc ions, concentration of zinc ion, we should put the unit, it is mole per liter, the variation of the concentration of zinc ion with time. As you know, zinc is a product, so at time equals 0, it is 0, the concentration is 0. It increases with time to reach a certain value. Here in this case, the concentration of Zn2 plus at T final is calculated and it is found to be 1 mole, so it remains constant at 1 mole per liter. Let's review some rules about calculating the concentration of certain solution. For an acidic solution, if the percentage by mass is given and the density and the molar mass, we can calculate the concentration according to a certain rule that we should always know. But this rule needs to be derivated. How can we derivate this rule? As we know, the percentage by mass is represented as mass. Here, since we have hydrochloric acid, it is the mass of hydrochloric acid over the mass of the solution. But we know that number of mole is mass over molar mass, so mass can be written as number of mole times molar mass. Substitute number of mass of HCl by number of mole times molar mass of HCl. The mass of the solution, also we know that density equal mass over volume, so the mass of the solution is density times volume. So substitute mass of the solution by density over volume. Also we know that concentration is number of mole over volume, so number of mole over the volume of the solution can be substituted by concentration. Don't forget to multiply by 100 since it is percentage. So number of mole over volume can be written as concentration molar mass over density times 100. This is the rule of percentage by mass, or a relation between percentage by mass, concentration, density, and molar mass. We can use this relation only if percentage, density, and molar mass are given. But here the question is to calculate the concentration. So concentration is percentage times density over 100 molar mass cross multiplication. By substituting the values given above, percentage is 34, density is 1120 gram per liter. You should always check the unit. If it is in kilogram per liter, you have to change it into gram per liter multiplied by 1000 over 100 times molar mass, which is 36.5. By calculation, we can get that the concentration is 10.47 mole per liter. But this concentration is very high for an acid. It is very dangerous to use an acid with this high concentration. So the only solution to use this acid is by diluting it. So if the question was, can you use this solution in any experiment? We can't use it since its concentration is high. You can use it only if we make first dilution. So in order to be able to use this very concentrated acid, we have to dilute it. Here it is given that dilution required is 20 times. From grade 10, you know that there is something called dilution factor. Dilution factor is the number of times we made dilution. Dilution factor can be represented as F or X sometimes or D sometimes, but the rule is dilution factor is equal to the concentration of the concentrated solution over the concentration of the diluted solution. Also, it can be written as volume, so it is volume of the diluted solution over the volume of the concentrated solution. So C0 V0 equals C times V. In this solution, the solution prepared above was known as S0, which has concentration C0 equal 10.74. We make dilution for the solution S0 20 times to get a new solution, which is known as solution S. Solution S is a diluted one. So what is the concentration of solution S? Since dilution factor is given, we can use it. Dilution factor equals C0 over C. We need C, so it is C0 over dilution factor. C0 is calculated as 10.74 over dilution factor, which is 20. The answer will be 0.537 mole per liter. This concentration of an acid is very suitable to be used in any experiment. Also, we have some rules which were explained in grade 10, but it is very important in grade 11, also in grade 12, as the preparation of solution S. Starting of any solution starting from a solid. Here we have a solution named S, which should be prepared from copper sulfate, which is a powder. We should know the concentration and the volume of the solution to be prepared. Solution S0 has concentration equal 1.5 mole per liter, and the volume to be prepared is 100 milliliter. What mass of this solid should we use in order to prepare this solution? Mass can be calculated according to this relation: mass equal concentration times volume times molar mass. If you want to know how can we get this relation, all of us know that number of mole is equal to concentration times volume. Also, you know that mass is equal to number of mole times molar mass. So the mass is, instead of number of mole, put C times V times molar mass to get this relation. This relation can be used without derivation. To calculate mass, concentration is given as 1.5, the volume is 0.1, change it into liter, it is 0.1 liter, and the molar mass is given at the beginning of the exercise, it is 160. By calculation, the mass is 24 gram. To know the material that we need in order to prepare this solution, we need of course a balance. It should be digital balance or sensitive balance, so we need a balance. We need watch glass in order to put this solid and weigh it. We need a spatula. we need a funnel in order to pour this solution into a volumetric flask. You should be careful to the volume of the volumetric flask. The volume of the volumetric flask should be chosen according to the volume of the solution to be prepared. Since we are preparing a solution of volume equal 100 milliliter, so the volumetric flask should have volume equal 100 milliliter. If you write volumetric flask without any volume, you cannot get any mark. Some other examples about dilution can be given as shown in this part. Always in case of dilution, we have two solutions: solution S0, which is the concentrated one, and solution S, which is the diluted one. How can we change solution S0 into S? Let's examine the given carefully. 250 milliliter of diluted solution S, so the volume of S is 250 milliliter. Always illustrate the given by a drawing, a certain drawing. The concentration is 0.1 mole per liter. What volume V0 should be taken from solution S0 in order to dilute it? So the question is to calculate V0. You know from the previous part, the concentration of solution S0 is given as 1.5 mole per liter. So a certain quantity of V0 should be taken from solution S0 and diluted many times in order to obtain a new solution S, which is the diluted one. So how can we calculate V0? You should write that during dilution, this note is very important. Without writing it, you will lose points. During dilution, number of moles of solute is conserved. You should write number of moles of solute. Not number of mole is conserved, number of mole of solute. So, since number of mole of solute, so the number of moles before dilution is equal to the number of mole after dilution. Number of mole after dilution. And we all know that number of mole is concentration times volume. Before dilution, the concentration times volume is for solution S0, so we write C0 times V0. After dilution, the number of mole of solute is concentration times volume for solution S, so write C times V. Concentration C0 is given, V0 is unknown. C and V are also given. By calculation, V0 equals C times V over C0. Substitute concentration, volume, and C0 by their exact values. Concentration is 0.1. Volume, change it into liter, it becomes 0.25 over C0, it is 1.5. By calculation, we get that concentration, the volume that should be taken, V0, is 0.0166 liter. Volume is given in liter. Change it into milliliter, it is 16.6 milliliter. This is a volume that should be taken. So what set or what glassware should we use in order to carry out this dilution? The most convenient set is set 1. Why set 1? In each set we have volumetric flask and a pipette. To know the correct volumetric flask, in set 1 and set 2 the volumetric flask is the same, since we have volumetric flask 250 milliliter and volumetric flask 250 milliliter. Volumetric flask, you should choose it according to the volume of the solution to be prepared or to be diluted. Yani volume of solution S. Volumetric flask is 250 milliliter, since we are preparing a solution of volume 250 milliliter, so it is correct. But which pipette do we need? According to V0, it is 16.6 milliliter. Volumetric pipette is not correct, so the most convenient pipette should be graduated in order to measure 16.6 milliliter. It is graduated pipette 200 milliliter, so set 1 is the most convenient one. Now we have a reaction taking place between Ni and copper sulfate. Since we have a solution of copper sulfate, Cu2 plus SO4 2 minus, and we put in it a certain quantity of Ni. The number of mole of copper produced is recorded in the graph aside, and Ni will become Ni2 plus and Cu2 plus will change into Cu. According to this graph, the value remains constant, the value becomes constant at 0.01. So this value represents number of mole of copper metal produced at T final. It is equal to 0.01 mole. The question is, time equal 20 minutes. At this time, the number of mole of Ni reacted after 20 minutes is equal to 8 times 10 to power minus 3 mole, which is equal to 0.008 mole. Does this value or this time represent the end of reaction? To know if time equal 20 minutes is the T final, we have to make a stoichiometric ratio between number of mole of Ni and number of mole of nickel and number of mole of copper produced. According to stoichiometric ratio, N of Ni over 1 equal N of Cu over 1, since the coefficients are 1. But we know that at T final, the number of mole of Cu is equal to 0.01. Number of mole produced at T final depends on the number of mole of Ni reacted. So we can get number of mole of Ni reacted at T final according to the number of mole of Cu given. It is equal to 0.01 mole, which is greater than 0.008 mole produced or reacted at time equal 20 minutes. So by comparing the two values, we can notice that T final is not 20 minutes. With respect to part 2.3, we have this relation. This relation is given as number of mole is 0.01 minus mass of copper over 64. You know that number of mole of copper equal mass over molar mass. So instead of mass, we can put number of mole times molar mass. So this relation is 0.01 minus number of mole of copper times molar mass, which is equal to 64 over 64. And the number of mole of Cu at T final is equal to 0.01 as given in the graph. So 0.01 minus 0.01 is equal to 0. So at T final, number of mole of Ni equal to 0. Ni is consumed totally. Since it is consumed totally, it is the limiting reactant. To complete this table, we have a certain given. X is equal to the number of moles of Cu of copper which is produced during the reaction at time t. But we know that at T final, the number of mole of Cu produced is equal to 0.01 mole. This is given in the graph. To complete this table, we have two instances, initial time and final time. We know that at initial time or at time equals 0, the products, number of mole of product will be 0. So Ni2 plus and Cu have 0 value. At the final time, 0.01 mole of Cu2 plus remain unreacted. And we know that at T final, number of mole of Cu is 0.01 mole. It is given in the graph. So number of mole of Ni is not given. Leave it as N of Ni. Number of mole of Cu2 plus is also not given. During the reaction, X quantity of Ni is reacted with copper to produce Ni2 plus and Cu. So Ni, number of mole minus X. Here, number of mole of Cu2 plus also minus X. Here we have X with X. But since Ni is limiting, so its number of mole at T final should be equal to 0. and X is equal to 0.01 mole. So X is given. Substitute the value of X. We can get that number of mole of Ni is equal to X equal to 0.01 mole. It is the initial number of mole of Ni at time equals 0. Also, number of mole of CO2 plus minus X is equal to 0.01 mole. So, number of mole of CO2 plus equals 0.01 plus X, and X is equal to 0.01. So the number of mole of CO2 plus is equal to 0.02. It is the initial number of mole of copper ion. For Ni2 plus, number of mole of Ni2 plus at T final is equal to X. It is equal to 0.01 mole. Now, how can we calculate the minimum volume of solution S? Solution S is a solution of copper sulfate CuSO4, which contains Cu2 plus and SO4 2 minus. How can we calculate the minimum value? Be careful to that minimum value of solution S. You know that Cu2 plus is excess, and if we add a certain quantity of copper sulfate, this quantity will not react totally. So what is the minimum volume of copper ion or copper sulfate solution that is needed to react with an Ni? To calculate the minimum value of the volume, we know that concentration equal number of mole over volume. Thus, volume equal number of mole over concentration. Concentration of copper sulfate, since it is solution S, and the concentration of solution S is given as 0.1 mole. The concentration of solution S is 0.1 mole per liter. So to calculate the minimum volume, we have to take care of the minimum number of mole of CO2 plus reacted. So we should use number of mole of CO2 plus reacted, not the initial number of mole, since we are calculating the minimum volume of solution S. The number of mole of CO2 plus reacted is 0.01 mole. It is equal to X. So the volume should be 0.01 mole over the concentration, which is 0.1. It is equal to 0.1 liter. It is 100 milliliter. It is the minimum volume. But if the question was calculate the volume of solution as added to the beaker at time equals 0, so we can use the number of mole of copper sulfate initially added. So we can use number of mole which is equal to 0.02. If the question was calculate the volume of solution as added to the beaker at the beginning of this experiment, we can use number of mole of copper ions initial at time equals 0, which is equal to 0.02. But since the question is calculate the minimum volume that should react with an I metal, so we have to use the number of mole of CO2 plus reacted. Be careful to this question. With respect to 2.5, we have to choose the correct answer. The color of the solution at the end of reaction will be colorless, light blue or dark blue. The solution is blue in color due to the presence of copper ions. Copper ion has a blue color, but during the reaction, CO2 plus are becoming Cu by gaining 2 electrons. So the concentration of CO2 plus decreases with time. Since the concentration of CO2 plus decreases with time, so the blue color will fade. It will become dark. It will become light blue. It is not colorless since CO2 plus is in excess. If CO2 plus is consumed totally, if CO2 plus is the limiting one, so we should choose the colorless answer. 2.52 the concentration of SO4 2-. How can we calculate the concentration of SO4 2-? SO4 2- is a spectator ion which is obtained due to the dissociation of copper sulfate into Cu2+ and SO4 2- by stoichiometric ratio at same volume. We can write concentration of CuSO4 over 1 equal concentration of SO4 2- over 1. Initially, the concentration of copper sulfate is equal to 0.1 since it is solution as, so the concentration of SO4 2- will be 0.1 mole per liter. Correct answer is A.